Welcome to these new sections of DAIDD2022 on seasonality and diseases. I'm Giulio De Leo, and I'm a faculty director of the program for disease ecology, health, and the environment at the New Door School of Sustainability of Stanford University. Before we get in the core of the presentation, let me set the stage. So, we have seen so far several deterministic autonomous models of disease dynamics. Classic SIR compartmental models of susceptible, infected, and recovered that has been described here on the screen. The variable SIR represents the state of the system at time t. Note that here the rates of change in time, the dx over dt, do not explicitly depend upon the time t. The parameter mortality rate mu, the transmission rate beta, or the transitions from infected to recover are model parameters that represent the rate at which epidemiological processes occur. In basic SIR model, they're generally assumed to be constant in time, so they do not change over time. And these systems are called autonomous systems. In reality, there are lots of reasons to think about. There are some underlying variation in time there. The most classical one you can think is that of environmental stochasticity, that erratic behavior of climate or changes non-deterministic year to year, or even within year fluctuations of the environment. That is usually modeled through probability distribution functions in a stochastic fashion. Of course, when we think about variability, we also think about climate change. This is a long-term trend in mean and potentially also in variance and other statistical properties of major climatic variables, such as temperature, precipitations, and humidity. And then we have seasonality, which is the periodic, repeated, and quite regular and predictable, most of all, patterns typically occurring every calendar year, and especially in the high latitude. And last but not least, I also want to mention other cyclical effects like periodic, also to some extent repetitive and more or less regular patterns of climate spanning time periods longer than one calendar year, and potentially even over several years or even decades. Typically El Niño and La Niña, or the Pacific decadal oscillations, that has a time period of 60 to 80 years, very long. So this lecture today is specifically focused about sustainability. And these are the questions we will address in this class today. What is the evidence of seasonal changes in disease incidence? What are the drivers of seasonality? How do we incorporate seasonality in our epidemiological model? What is the effect of seasonality on the dynamic of infectious diseases? Does the shape of seasonality matter? And what are the implications for disease control and eradication? Just want to briefly mention there are plenty of reference of seasonality in diseases. One I like particularly is here in Rohani, the seminal texts on modeling infectious diseases, chapter 5. Also a beautiful paper by Sonia Altizer et al., published in Ecology Letter in 2006. And then other papers that are mentioned here in the literature. So let's start from the point. What is the evidence of seasonal changes in disease incidence? I think that everybody has somehow experienced, especially in the living temperate zones, of seasonal flus. And this is quite common, and there is plenty of evidence like this one from the US Center of Disease Control showing the activity peak month in the US are typically between January and March, with February being the month in which most frequently the seasonal flu incidence peak. So it's very strong evidence, and it's not only about influenza. There is certainly a malaria season as well, which is typically strongly connected with the rainy season. And there are other fingerprint of effect of seasonality in diseases, and some of them are really surprising to some extent. I just want to mention one that is the inverness transhumance in Sardinia Island, with these basically migrations of shepherd with the flock that it typically occurs from the low land, especially during the winter time, up in the highland during the summertime, to try to track basically the pasture. In Sardinia, on the other hand, it happened quite the opposite. That's why it's called inverse transhumance, with permanent settlement in the highland and seasonal movement of flocks in the lowland in winter, which as one of the driver, they also tend to avoid the summer high transmission season that was occurring in the lowland. So with the permanent settlement always establishing in the island to try basically to escape malaria. This is certainly, an historical case that have a strong influence on the habit of this population in the Sardinia island. But the understanding that seasonality might have an effect on disease dates back really a lot more than 2,000 years. For instance, from Hippocrates, that already observed relationship between weather and diseases. And back in the 1600, Sydenham commented on seasonal and recurrent epidemics. In 1740, Hillary, for instance, published an account of the principal variations of the weather and the concomitant epidemical diseases that is there. And Hirsch in 1885 commented the seasonality of measles, typhus, typhoid, yellow fever, and cholera. And Soper in 1929 published a paper on the interpretation of periodicity on disease prevalence. Basically, he observed and was wondering why, in direct contrast to the classic SIR model projections of dampened oscillation in time, multi-year periodicity, that is, outbreaks every few years, like every 2 or 3 years, were actually observed, for instance, in Glasgow. So the data basically were reporting patterns that the classic susceptible infected model was unable to reproduce. He suggested, in fact, that a missing ingredient in basic model was seasonal changes because of the perturbing influences, such as might be brought about by school break up reassembling or other annual recurrences. Since then, a large body of work has demonstrated the influence of seasonality on the dynamics of measles, pertussis, chickenpox, rubella influenzas, like represented, for instance, in this paper by Dowell, published in 2001, where Dowell observed also that there is a very strong relationship, for instance, of poliomyelitis with the latitude, both going in the northern latitude and the southern latitude, which speak in exactly, the opposite, basically, month for tracking basically the warming season. Another very interesting data-driven paper, for instance, is this paper by Sultan on climate drives the meningitis epidemic onset in Western Africa, where Sultan and his co-author observed and quantified statistically that the week of epidemic onset of meningitis was strongly related. We're talking about 92% correlation with the week of the stronger winter wind. So with a really strong predictable patterns and effect of seasonal wind on the onset of meningitis epidemic. There are lots of other anecdotes that I just want to mention. What we most mentioned so far, for instance, were like influenzas or malaria, but here we see another acute contagious viral diseases, small ruminants, the petit ruminant, whose outbreaks are associated with the onset of the rainy season or dry cold periods, very clearly shown by the data. And this is true also for gastrointestinal nematodes, for instance, in the case of infection in sheep, in which there is clearly a very significant seasonal variation. And If you're not convinced enough, I strongly suggest you to have a look at the beautiful paper by Sonia Altitzer, The Seasonality in the Dynamics of Infectious Diseases, published in Ecology Letter in 2006, where you will see a full analysis of the impact of seasonality on wildlife diseases and human diseases as well, and a list of the diseases, the timing of the outbreak, and the mechanism of seasonality. So we can say there is plenty of evidence for seasonal trends in recurrent epidemics. So the obvious next question is why? Why is that the case? Why? What mechanisms drive seasonality? Well, a very clear one is host behavior. Anything, especially like for the human host, for humans, national feast, public event and ceremony, school terms, any event that aggregate people increases for very clear reason the contact rate, and that is one of the basic ingredient of epidemiology. If you increase the contact rate for infectious diseases, for communicable diseases, you increase the opportunity for the pathogen to move from an infected host into a susceptible host and infected host. So very clearly and strongly demonstrated by the data. In general, seasonal and environmental fluctuation of environmental drivers like temperature, like precipitation of wind, have a strong effect on the distribution of species, for instance. They might cause aggregation of species in the water pool during drought, and so increasing once more the contact rate for communicable diseases. In some cases, they might trigger large-scale migration. Other cases, they might change the availability of resources. And so with this one, also, they're changing the abundance of the host and have an effect on the seasonal dynamics of the disease. And in other cases, they might just percolate the seasonal effect of these environmental drivers through the food webs into very different and subtle ways. There are processes that are important for parasite transmission. There is effect of seasonality, variation of physical parameter, again, like temperature, humidity, rainfall, salinity of flow, on Vibrio cholera, on nematodes free living stages, for instance, and vector survival. And it's interesting, as you can see from Altitzer paper in 2006, is that the seasonality of the vector might be different to the seasonality of parasitic stage of the host. So there might be phase displacement among them, and so the effect is not always completely obvious. The hot birth rate is typically seasonal, especially in places that have a strong seasonality in climates or in temperate zones. And this might percolate and trickle down also to the strength of the immune response. And so even when population size is apparently constant, the susceptibility to pathogen might change because of a change of resources, for instance, that might have an effect on the immune response. So the next question here is how do we incorporate seasonality in our model? And we take a little break to move to the next section.